Hi everyone, welcome to the Wednesday Chem Help ASAP live stream. As you can probably tell from the title here, we are going to be doing a little bit of nuclear chemistry. So most of this time is going to be spent on reviewing the different particles and writing nuclear reactions, though at the end we will do one calculation where we will calculate the energy associated with a fusion reaction. Okay, so let's just go ahead and jump in. All right, so the first thing I have here on the left is this big table. This summarizes most of the most common particles. Of course, there are always different kinds of particles, but these are the most common. So not only do I give you the name of the particle, but I also give you its composition. So remember, when an element is written like this, you have your mass number up here and your atomic number down there. So we've got an alpha particle, a beta particle, a positron, an electron, a gamma ray, and a neutron. And it's important that we get especially the mass numbers for these, but also the atomic number. So, and you can see like some of these are the same. So a beta particle, if you look at this, is the same as an electron. So sometimes in problems, you'll see it just an electron referred to as an electron, or you might see it referred to as a beta particle, but I want you to be able to go back and forth between both of these, and so you know the names for both. So what I thought we would do is just start with one question and then move on from there. Okay, so the question I have here is write the nuclear reaction of a carbon-14 atom that undergoes beta decay. So we've got a couple of pieces of important information here. We're going to start with a carbon-14 atom. We've got a beta particle, which again, we know what it is, and it's going to undergo decay, which means the beta particle is going to be on the product side. So let's go ahead and get some things writing here. Now, carbon-14, of course, when in problems, a lot of times you'll see it written kind of with words like this, but I am actually going to write it much more like this guy here. So 14 is my mass, and of course, it is a carbon atom. Now, what I want to do here is I want to be able to add the atomic number. So I did pop a periodic table right here. Okay, so if you find carbon on the periodic table, of course, the atomic number is always going to be given. So the atomic number is 6. So sometimes in these problems, you will be given the atomic number, and sometimes because you're given the element, you will be asked to come up with the atomic number. So that's why I've got the periodic table here that we can refer back to instead of trying to squeeze it in on that page. Okay, so we're going to have a 6 there as our atomic number. So I'm going to put the 6 down here for carbon. Okay, so here is carbon-14 written how we want to write it as we're writing our reaction here. And it's going to undergo beta decay. Again, that means that the beta particle is on the product side. So I'm just going to write the beta particle as we have written it here. So it's an electron, mass number of 0, and the atomic number of -1. Now, then we're going to have plus something, and we don't know what that is quite yet. Now, when you're doing these reactions, the important thing to remember is all of your mass numbers and all your atomic numbers on both the reactant side and the product side need to equal. So I'm going to start with my mass number. So because I just have carbon on the reactant side, my mass number, of course, is 14. So I need to make sure that my mass number here plus, well, 0 is 14. So that's easy. So I know that my mass number for whatever else is formed here is going to be 14. Because again, this 14 has to equal the sum of these two right here. Okay, the same is true for our atomic numbers down here. So I have 6 on the reactant side, and I've got -1. Again, this is really important that you know what charge is here. So I have a -1 here, so I need to put a number here that plus -1 is going to give me 6. Well, of course, that is going to be a 7. So 7 plus a -1 will equal a 6. So now I have all of my numbers are equal on both the reactant side and the product side. Now, the nice thing about having our mass number done is our mass number is 7, sorry, not our mass number, our atomic number is 7, and that gives us the identity of this other atom. So remember 7, let's go back to our periodic table, and if we find atomic number 7, you can see right here it is nitrogen. So I can simply write an N there. So this is obviously an easier one, but I hope this makes sense. We're going to practice a lot more of these. And again, the key is that you can even think of it as the top numbers up here have to equal and the bottom numbers down there have to equal. Again, however it makes the most sense to you. All right, so that was our first reaction. But let's do some more. We'll keep this periodic table because we'll flip back and forth to it often. All right, so I still have my table on the left, which gives me all of my particle names and mass numbers and all of that good stuff. So my next question is, when uranium-235 undergoes alpha decay, what is the daughter nuclide? So again, we've got alpha, so we know we've got an alpha particle. We have a decay, which means it is going to be on the product side, and we are starting with uranium-235. So again, I want to write that uranium-235 not with words there, but with our symbol. So 235 is our mass, so it goes on top. And of course, this is uranium. Now, what I need to do is I need to find my atomic number first. So I'm going to go back to my periodic table. And if you find uranium down here in the F block, here it is right here. And so my atomic number is 92. So I'm going to put a 92 here. Okay, so it is going to, again, undergo alpha decay. So I need to now go to products. All right, so my alpha particle is given to me right here. It's just a helium atom. So I'm just going to copy that down. Here is my alpha particle. So now what I need to know is what else do I have right here? And again, remember, your numbers need to be equal on reactant side and product side. So what I need is I need 235 here to equal 4 plus something. Well, this has got to be 231. So now I have 231 plus 4 is 235. And of course, I only have 235 on the reactant side. So those are equal. So that's great. Now I need to do my atomic numbers. Okay, so I only have uranium, and that's 92 right there. So something plus 2 must equal 92. Of course, that's 90. The nice thing about these is the addition subtraction is pretty easy, but sometimes keeping track of where everything is can be difficult. So now I just need to identify what this element is. And now that I have the atomic number of 90, I can go back to my periodic table. And if you find 90, it's right down here. So this is thorium. And that is my reaction. Okay, let's keep on going here. Okay, so write the equation when chromium-51 undergoes electron capture. All right, so I have chromium-51. I've got an electron, and it's an electron capture, so it is not a decay, which means my electron is not going to go on the product side, but it's going to go on the reactant side. So this is electron capture, not what we would probably call beta decay. Again, this is where the language can get a little bit confusing. All right, so we've got chromium, and its mass number is 51. Let's get its atomic number. Okay, chromium. Here it is right up here. Atomic number 24. So let's get that in. Okay, again, this is electron capture. So this is going to go on the reactant side. Here is my electron. This gives me what I need, the information I need here. So we have a 0, a -1, and an E. And now we are going to predict products. All right, so again, in our previous examples, our reactant side was just one atom, and our product side, we added things together. But this is going to be reversed. We're going to add things together for our reactant side, and that's going to help us predict our product side. All right, so we have 51 and 0, which is just 51, which means on my product side, my mass number must be 51. And then I've got 24 plus a negative 1 gives me a total number here of 23, which means I need a 23 over here. That is my atomic number. And feel free, I like to do these little side calculations just to kind of keep track of where everything is. So I'm adding in the right place and subtracting in the right place. But let's identify this atom. So our atomic number is 23. So we need to go back to the periodic table. And if we find 23, here it is right here. This is vanadium. All right. So that is our reaction. All right, so these hopefully are making a little more sense, but it's all about practice, practice, practice. All right, so let's read this guy here. Neon 22 is formed from positron production. Okay, so we've got a positron. Write the equation for this transformation. All right, so this one is a little bit different. So we've got to be careful. So neon 22 is formed. So that means that neon 22 is a product. I'm actually just going to go ahead and write my arrow and make sure that I get neon on the correct side. Okay, let's get our atomic number for neon. So back to, oh wait, I think I have a periodic table. Yes, I scattered them kind of throughout my slides here. So we need neon, that's a noble gas. Here we are right here, so it's atomic number 10. All right, so I've got neon in the right place and I've got all of my information. Now we're dealing with positrons, which we have right here, but this is positron production. So I need to make sure that I put it on the, not the reaction, the product side. So we are producing a positron. So I'm going to go plus this. Again, I'm just pulling from positron right here. And so what I'm trying to figure out is what I started with. So this is where I feel like these reactions can get a little bit tricky, is you just have to make sure you know, are you talking about reactant? Or are you talking about a product? Are you talking about a decay or a capture or a production? And just making sure you're really careful with reading the language and putting things on the correct side. All right, so let's actually predict what this is. So of course 22 plus 0 is 22, so I know my mass number is going to be 22 right here. And with positron production, this is a positive 1. So 10 plus 1 is 11, which means I need to have an 11 over here on this side. So now that I have the atomic number, I can identify what element this is. So let's go back to our periodic table. Now, the nice thing is when you're doing these problems, you don't have to switch back and forth between slides. Just keep, your favorite periodic table right there. So we had an atomic number of 11. So if we find atomic number 11, you can see it's right over here on the left. It is sodium. So now I know the identity of that element, and that is sodium. Okay, so I've got a little bit longer one here at the bottom of the page. All right, so uranium-238 produces an alpha particle, 2 gamma rays, and a daughter nuclide. Write an equation for this transformation. Okay, so I've got more than just one thing going on here. And again, I need to make sure I keep straight what's on the reactant side, what's on the product side, and what I am trying to predict here. Okay, so uranium-238 produces all of this. So uranium-238 is going to be on the reactant side. Let me go ahead and get that in. So we're going to have 238, of course, is the mass, and we've got uranium pops up a lot in these kind of questions. And let's go ahead and get the atomic number again. So we found it before, so let's just find it again. Here we go, atomic number 92. Let's get that in there. All right, great. Okay, so basically what we've got is uranium-238 is going to decay into a couple different particles here. So we're producing an alpha particle, which of course we have right here. So let's just go ahead and get this helium atom in, this alpha particle. All right, great. Plus 2 gamma rays. Okay, so here are gamma rays. Now the good thing about gamma rays is it's just 0 and 0. So gamma, oh, you know what I need to do? I need to put a 2 in front. See, I already forgot. Okay, 2 of these guys, 0, 0, and gamma. And we have some kind of nuclide here. So we've got a question mark or a blank. All right, so we've got a couple of things to add up and keep track of. Now again, even though we have two of these, because both the mass and atomic numbers are 0, that makes our math a lot simpler. So we really just need to worry about this alpha particle. All right, so on the reactant side, of course, we have 238, and right now we have 4 on the product side. So we need a mass number of 234 to make sure that those are equal. And then the same thing is going to be true for our atomic number. So we've got 92 and then 2, and of course that's 0. So this must be a 90, which means we can now identify this atom. So we just need to go back to our periodic table, and we're looking for atomic number 90, which is down here. Here we go. It's thorium again. A lot of times in these nuclear reactions, you do end up going to the very bottom of the periodic table where maybe you felt like you hadn't spent a lot of time before. Okay, so yeah, okay, just want to make sure there were no questions. I realized I hadn't checked the chat in a little while. Okay, so those are those reactions. Let's go on periodic table. Okay, so now we get kind of a bunch of reactions, and you can see these get a little more complex, and we're going to have to deal with just more numbers and keeping track of things. All right, so we're just going to go one by one. So let's go with our first reaction. I think I'm actually going to just rewrite it instead of trying to squeeze everything in there. So this is going to produce 3. That is germanium, and then we need to predict whatever is over here. So at least this one we are given the atomic symbol, so that's great, but we need to find our atomic numbers. So let's go back to our periodic table. So we've got Ga, which is gallium, which is right here, and so it's got atomic number 31. So let's get that in there. And then we've got germanium right here. So let's go find that and get its atomic number. It's very close. It's right next door. Here we go. Here is germanium, atomic number 32. This is the great thing about the periodic table. You never have to memorize these at all. Okay, so now we need to figure out what is going on here. Presumably what particle have we emitted here, or what kind of decay has it gone under. So I see that I've got 73 and 73, so the only choice I have is to put a 0 up here. And now I've got 31 and 32, so to make these equal, I've got to have a -1 here, and then I have 31 and 31. Now, I already recognize this as a positron, but in case you don't, I'm just going to pop back to my table here. So if we had a 0 on top and a -1 on bottom, and sorry, not a positron, a beta emission, you can see it's right here. And so that is going to give us an E. And of course, we don't actually even have to name it, but you can if you want. All right, so that is our first reaction done. Let's move on to our second reaction. Okay, so again, I'm just going to recopy this. All right, so we've got platinum, and we're going to osmium. And then again, we have plus, and we've got a blank here. Okay, so let's first platinum. Let's find platinum. Okay, so platinum, up there's palladium, here's platinum right underneath. I don't know about you guys, but I always tend to mix up palladium and platinum. So platinum is atomic number 78. All right, great. And then next we have osmium. Osmium, I know, is right in the middle somewhere. Here we go, right here, number 76. And don't worry if these take a little while for you to find. Sometimes I just can't find them, and it takes me a while to find them as well. All right, so now that I've got all my numbers in, let's predict what's going on here. Okay, so I've got a 192 over here on the reactant side and a 188. So to get to 192 to make these equal, I'm going to have to add 4 here. Yes, because 4 plus 188 is going to give me 192. Okay, and then I've got a 78 down here and a 76, which means I need a 2 here for an atomic number, and then 2 plus 76, 78. So I'm all equal here. So I've got a 4 and a 2, which again I recognize as an alpha particle, but in case if you're not as familiar with it, you can see here 4 and 2 helium atom. This is my alpha particle. So I just need to write He right here. Now you can also there's a little bit of a shortcut because we have an actual atomic number. You can see helium here does have an atomic number of 2. So you can actually get to that 2 different ways, again, whichever way makes the most sense to you. Okay, let's go on to our next reaction. So we've got 205. This is bismuth, and we are going to go to still 205, but now we've got lead. And again, we've got a blank to fill here. So let's go ahead and get atomic numbers. All right, so bismuth. Here we go, down here, atomic number 83. Great. And then we've got lead. So that's in about the same place. Here's lead, and you can see it's atomic number 82. That is great. Okay, so now we have all of our numbers in, and we just need to make sure that they are equal. Okay, so 205 and 205, I've got to have a 0 here. And then 83, 80, I need to have a 1 here. Yes, 82 and 1 is 83. So if I go back to my table and I'm looking for a 0 and a 1, I'm going for a positron emission right here. So I'll put a little E down. Okay. Let's go on. So I can see that like these first 3 reactions, again, were pretty simple. They were just maybe a little step up, but it looks like these next 4 are going to be even more complex, and we've got multiples here. So I can already see like I've got 6 neutrons coming in right here. All right. So again, I'm just going to rewrite so I've got space to do what I want. Okay, so at least for this reaction, they did give us the atomic number of 92 for uranium. Again, some questions will give you that and some will not. Okay, so, and then here is carbon. Okay, I'm trying to predict this, and I have 6 neutrons going on here. All right, so the important thing here is this 6 is a multiplier for this 1 here. Well, it is also for the 0, but obviously that doesn't mess with anything. So what I've got for kind of my blank spot here is I have my 238 plus 12, which was going to give me, you know what, I'm going to put this in a different color. So this is a little bit, again, this is where I like to do just some notes for myself so I keep track. That is going to be 250. Okay. And then, of course, I've got 1 times 6, which is 6. Maybe I'll stick with my green. So that's going to give me 6 plus something has also got to equal 250. Sometimes even just writing it down is helpful. And so that is going to be 244. Okay. Again, that green, those are just my side reactions. So I'm going to have a mass number of 244. I'm actually going to get rid of this so I can write over it. And now let's do the same for the atomic numbers. These are a little smaller. These are a little bit easier to do. And of course, 6 times 0 is just 0, so I don't have to mess with the neutrons in this case. So I have 92 and 6, which is going to be 98, which this is going to have to be a 98. All right, so now I have my atomic number, which means I can identify this atom. So let's go back to our periodic table, and we're looking for 98, 98, 98 down here, and it's californium. All right, so that is going to be a CF. Okay, great. So you can see these have kind of stepped up just a little bit in terms of their difficulty. Let's keep on going. All right, so in this next reaction, I am predicting right off the bat. So I've got a blank here. And in this case, I am not giving off an alpha particle, but I am actually capturing an alpha particle. Okay, so 243, 97, that's berkelium. And we just have 1 neutron here. Okay, no problem. Okay, so let's do some addition, subtraction, right? Okay, so I've got 243 plus 1. Again, I'm just going to switch to green so I can keep track here. That is 244 total up here for my mass number. I've already got a 4 here. That means I have got 240 for my mass number. And now let's go ahead and do my atomic numbers. I've got 97, and that's 0. I already have a 2 here, so that is going to be a 95 to make sure that these are equal, which means I now can identify my atom. Okay, so atomic number 95. Let's find that. 95 is americium. So AM. All right. Okay, that one is done. Let's keep going. Okay, so rewriting this. 249, 98. We've got another Californium. I've got a blank here. I'm not sure what that's going to be. And then 260, 105. I'm not sure what dB is. I'm going to have to go look that up. But we'll be back to the periodic table shortly. Okay. All right, so let's figure out what our mass and atomic numbers are. Again, remember you've got this multiplier of this 4 here for these neutrons, so it's not just 1, but it's 4 times 1. All right, so that means that I have 260 plus 4 is going to be a 264, and I've already got 249 here, so that is going to give me a 15 for a mass number. And then for atomic number, okay, that is just 0, so I have 105. I already have a 98 here, so that is going to give me a 7 for an atomic number. And let's go back to the periodic table, find atomic number 7, and it is nitrogen. Okay, that reaction is done. We've got one more. All right, so we've got Californium again. And 98. And now we've got boron. Okay, so we're bringing boron in. And we want to predict what that is. And we've got a 257. That is a 5. And atomic number of 103. I think that's lawrencium Lr, if I'm correct. Okay. So again, let's add our numbers up and make sure we get our math right. So I have 249 plus 10 is going to be 259. I already have 257 here, so that is going to be a 2. Then down here, I've got 103, and I've got 98 and 5, so that's already 103, so that is actually going to give me a 0. Aha. All right. So initially you might think I don't have a particle that gives me a 2 and a 0. But I do have neutrons. You can see them all scattered over here that give me a 1 and a 0. So what I think is going to be better to do is to erase the 2 there, make it a 1, and we are going to emit 2 neutrons. So that's where you don't always have to get the exact right answer, when you're doing these. This one you might have to look at and go, 2, well, that doesn't make any sense. How can I make it 2? But again, you can emit as many of these particles as you want. I mean, you can see up here in this reaction with uranium, we emitted 6 neutrons. So it's always good to remember that. And again, that's why it's good to practice these. Okay. Before I leave this slide, I just want to make sure. Oh, so we do have a question. Okay. Can any 2 elements be combined or any element be split, not just the highly unstable ones? Erin, that's a very good question. So the larger atoms, or the atoms with a really large nucleus, tend to be unstable, and they just tend to split on their own. This is radioactive decay that happens all over the place. But with enough energy, theoretically, you can combine any 2 atoms that you want. Now, this is how these low level down here, these elements are synthesized, is they basically just bombard different elements and try to form a a nucleus that's stable for a specific number of times so they can actually measure it. But, these nuclei down here are so big, they do decay very, very quickly. I wish I could give you a number for that. But again, theoretically, with enough energy, you could form just about anything. And a lot of these elements that we see on the periodic table, of course, come from supernova explosions where you've got a lot of energy and a lot of pressure and gravity working. But in terms of here on Earth, it's a lot more difficult. So I hope that answers your question there. It's a very good question. Okay, so yeah, this is really the other, this is a completely different type of question, but I just wanted to go over it. So this is where we've got a fusion reaction. So let me actually just first read the question. Okay, so calculate the energy released when you have 1 mole of deuterium, which is this guy right here, and 1 mole of tritium, which is this guy right here, undergoes a fusion reaction like this. All right, so fusion reactions, just like fission reactions, release a tremendous amount of energy. So what this question is asking is saying, hey, you've got a mole here. How much energy is going to be released if I can fuse this mole together, this mole of reactants together? All right, so to do this, we need to have the mass of all of the particles that are a part of this. So that's why we have this table here. So you can see I've got all of my particles that are in my reaction, and I am given the mass of all of them as well. And what we will see is we're going to add up the mass of our reactants, we're going to add up the mass of our products, and we're going to see that they are not equal. There is a difference in mass. And what has going to happen is you're going to see that the mass of the reactants is actually larger than the mass of the product. So we have lost mass in essence. But what we've really done is we've taken that mass and we have transformed it into energy. But that goes on to the next step. Let's first just get the mass of our reactants and our products. So let's start with our reactants. So I'm starting with these two guys here. So let's go. Reactants. So, and the nice thing is, we just have one of these. We're just dealing with 1 mole. So we've got a lot of ones in here, which help make things very, very easy. So I am just going to add these two masses. So I'm going to have 2.01410 AMU plus my tritium is 3.01605 AMU. And if I add that together, then I get 5.03015. That is AMU. Kind of ran out of space there. All right. So that is the mass of my reactants, and let's also get the mass of my products. So I've got my helium atom, or my alpha particle. All right, so this is products. So that is going to be 4.00260. This is where, it's really important that you can measure these masses out to many decimal places, because we're going to see that the difference in mass is actually really, really small. Okay, so we've got that, and we're adding in the neutron, which I'm given right there. So that is 1.00866 AMU, and that gives me 5.01126 AMU. Okay, so again, you can see that the mass of my reactants and the mass of my products are not the same. So what is the difference between these two masses? So we're just going to subtract those two numbers, and we get a difference in mass of 0.01889 AMU. Now, depending on how recently you have used AMU, AMU is equivalent to grams per mole. So we can always also write this as 889 grams per mole. Now this is where having the 1 mole is so helpful. So if we have 1 mole of these reactants, it means that our difference in mass between reactants and products is simply this number times 1. So our difference in mass here is 0.01888 grams. All right, so we have a difference in mass. We have lost mass, and that mass has been converted into energy. So this is where we're actually going to use Einstein's most famous equation, E equals mc squared. So you see this plastered everywhere, and everybody talks about it, but now you're actually going to do a calculation with it. So we are going to calculate the energy associated with this loss of mass. Now, what we need to do to make our units work is we need to convert this grams into kilograms first. All right, so all we're doing, of course, is just go ahead and set this up. So there are, of course, 1,000 grams in 1 kilogram. So we are dividing by 1,000 to convert this. That is a comma that looks like a decimal, to convert this from grams into kilograms. And it's going to be much easier to use scientific notation here. So 1.889 times 10 to the negative 5th kilograms. All right, so that is our mass. We know the speed of light is 3 times 10 to the 8. So we are literally just going to plug this in. All right, so we have our mass. And of course, this is a tiny, tiny mass. But we're going to get quite a large number out of here. Now, the speed of light is meters per second, and we are going to square that. All right, so when you do this calculation, you're going to get an energy, and that is 1.7 times 10 to the 12th. Now, remember I had to change this into kilograms, and I'll tell you why. So my units here are kilograms times meters squared over seconds squared. And the key thing about that is 1 kilogram times meters squared over seconds squared is equal to 1 joule, which you're probably more familiar with as a unit of energy. So the energy released here is 1.70 times 10 to the 12th joules. That's a tremendous amount of energy. Again, this is just for 1 mole. So if you think about, this kind of fusion, there are a lot of reactions going on in any star, but this kind of fusion happens. This is a tremendous amount of energy for a very small amount of material. And of course, stars can be incredibly massive. So this is why these fusion reactions just generate so much energy. This tiny, tiny little loss in mass results in this tremendous amount of energy that is released. So anyway, congratulations, you have used Einstein's most famous equation to actually calculate an energy, which I think is kind of cool. Okay, let's make sure there are no questions. Nope, there are no questions. Well, thank you guys so much for joining me for the live stream. If you have any requests on topics that you would like me to cover or questions that you would like me to work out, just give me a comment in YouTube or Facebook, or you can email me or whatever you would like. Thanks so much. Good night. Bye.